Pluto is a far-off and stealthy, more humble planet that once belonged to our closed planetary gathering. However, advancing obnoxious statements by Neil deGrasse Tyson, a leading astrophysicist, Pluto has been brought back into the spotlight by Tyson and Midiaku with a stunning disclosure. They propose that this cold world is on a possible crash course with Neptune. But how exactly would this actually work? And what might happen as a result? Are we witnessing such a massive event as an enticing and valuable distinction? Or is there another reason for this approaching perpetual mishap? Join us as we investigate the potential outcomes of a collision between Pluto and Neptune. The past planet, subsequently reclassified as a dwarf planet, remains a subject of focus and interest in the vast universe. As shown by ongoing estimates by leading experts, Pluto's orbit is hazardously close to Neptune's. Astrophysicists Michioku and deGrasse Tyson are both raising the alarm about a potentially dangerous interaction between these two planets, one that could be extremely hazardous for Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike any other planet in the group of nearby planets. It requires a stunning 248 years to complete one orbit. Since its discovery in 1930, it hasn't even completed a single revolution. But the fascination does not end there. Pluto's orbit is distinguished by its unusual elliptical shape, meandering widely from the almost round orbits of the major planets. What makes Pluto's orbit even more extraordinary is its inclination, which is tilted at 17 degrees to the ecliptic plane. Pluto's path, as it travels, is significantly more extreme than that of planets with this tendency. This extravagance adds another layer of complexity to its orbital plan. One of the most fascinating features of Pluto's orbit is its intersection with Neptune's. For approximately 20 years per orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its initial discovery. Astronomers tried to figure out its unique path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit maintains stability even while crossing Neptune's. Amid these complexities, Pluto's path is proof of the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to guess where they'll go based on where they started and how they pull on each other. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in an intricate manner. The terms non-synchronous vibration, orbital precession, and VZK oscillation are important for solving this puzzle. According to astrophysicists, what maintains the orbits of all the planets is non-synchronous vibration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from merging. Orbital precession, on the other hand, is used to describe the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, offering an additional layer of protection from potential collisions. Another key factor is the VZK oscillation, present in this circumstance. Named after three researchers, Zell, Kai, and another, who studied how objects move in space, it involves how three space objects like Pluto, Neptune, and the Sun rely on one another due to their gravity. This gravitational pull influences how they move. In Pluto's case, the VZK oscillation helps us understand why its orbit close to the Sun is so irregular. Despite Pluto's path appearing whimsical, this oscillation helps keep it moving smoothly for long periods. The VZK oscillation demonstrates that, although things in space may seem turbulent and unpredictable, certain patterns and rules keep everything in balance. These factors help keep Pluto's orbit stable, ensuring that it does not collide with Neptune or drift off course. This three-body problem is critical to understanding how space affects the way orbits change. Studying this helps us learn more about Pluto, our local planetary system, and even distant worlds and their stars. Mathematical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is actually unstable, where small variations in initial conditions can lead to huge differences over thousands of years. However, these peculiarities in Pluto's orbit have been found to maintain stability over incredibly long timescales. Monitoring this disruption has been crucial. Later automatic examinations have helped us understand how giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a special relationship with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. But Neptune is not the only planet at play. Jupiter's gravity also plays a massive role in stabilizing Pluto's orbit. Saturn contributes as well. These studies show that Jupiter's immense gravity is powerful enough to make sure Pluto stays on a regular path for an extended period of time. So perhaps Neptune, Saturn, and Jupiter are collaborating to ensure Pluto continues to move safely through space. Running into a problem. These differences are essential for preserving order and stability in space. Without these elements, the known solar system would be a much more chaotic place. Pluto-sized bodies could collide with others or be thrown out of their orbits, triggering a chain reaction with other celestial bodies. Pluto, in particular, with discussions about its possibly upcoming collision with Neptune, makes understanding its orbit crucial. This gives a clearer picture of the dynamic nature of the solar system. In the case of Pluto, it shows how even the most seemingly unstable orbits can reach a state of harmony through the complex interaction of orbital forces and gravitational mechanics. It also highlights the significance of constant observation and investigation of these phenomena to better understand our place in the universe. Investigating the depths of space frequently forces us to confront the strangeness of the heavens and Earth. Moreover, Pluto's orbit is an ideal illustration of the unpredictability of orbital chaos, which refers to the delicate reliance of a celestial body's orbit on its initial conditions. This is clearly illustrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computer simulations has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune pull on one another. By tweaking small details in the simulations, space researchers can see how even minor changes can greatly affect where Pluto ends up. In the late 1980s, these simulations showed something intriguing about Pluto's orbit. Despite having characteristics like non-synchronization, vibration maintenance, and orbital progression, Pluto's orbit can still be erratic and unpredictable. If you start with even a tiny difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after just a few years. But even with this chaos, Pluto's orbit persists for very long periods of time. This basically took billions of years, meaning that Pluto's journey around the Sun still has a certain order to it, even though it initially appears violent. Predicting particular celestial events, when they involve erratic orbits like Pluto's, is a huge challenge. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While mathematical models provide excellent tools for understanding and predicting the upcoming routes taken by celestial bodies, they also highlight the limitations of our ability to predict. These models depend heavily on the accuracy of initial conditions, and any small mistake or distortion can result in enormously different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of planetary orbits like Pluto's reminds us of the ever-changing dynamic nature of the universe. While we've made huge strides in understanding space, Pluto's case reminds us how much our current understanding of the universe remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and trajectories of other bodies within the framework. So why do they lead? Astrophysicists have recently raised concerns about a potential crash between Pluto and Neptune. Despite all these complex forces working to prevent such an event, Neil deGrasse Tyson, a prominent astronomer and a pivotal figure in promoting cosmology, provides a one-of-a-kind perspective on the mysteries of our solar system. The case of Pluto, in particular, is captivating. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, offers insightful perspectives on the evolving nature of celestial mechanics and the public's interest in neglected areas of space. His position regarding the renaming of Pluto is based on the ever-expanding knowledge of our solar system. He sees the renaming not as a reduction, but as an essential adjustment in alignment with our growing comprehension of the various bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous change. His perspective on orbital complexities like Pluto's is a sign of how much there is still to discover in space. These questions keep space exploration so fascinating. However, despite Tyson's confidence in his opinions regarding Pluto and its potential impact on Neptune, other illustrations of his concerns about Pluto's orbit suggest that there might still be some more secrets to uncover. Will Pluto collide with Neptune? Or is this just another moment of confusion in a constantly shifting universe? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we know about our solar system. We keep studying these phenomena in the hope of uncovering more of the mysteries that lie beyond. The possibility of a Pluto-Neptune collision raises yet another question about the enigmatic and captivating universe in which we exist. The potential for such a collision raises fascinating issues about the dynamics of the solar system, as it challenges traditional understandings of planetary stability. The idea that two celestial bodies with such disconcertingly different properties could collide is both unsettling and intriguing, especially considering the current relative strength of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is itself a massive gas object with a powerful gravitational field, the implications of such a collision would be extremely beneficial to our understanding of gravitational interactions and the evolution of the solar system. To comprehend the complexities of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains a variety of elements and substances that are thought to be in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere made mostly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is mainly composed of hydrogen, helium, and additional lighter elements that form a dense atmosphere. A collision between such disparate bodies would drastically influence their behavior and structure, possibly making the event obvious over great distances. What makes this possibility so captivating is the influence of other planets and bodies in the solar system. While the gravitational pull of Neptune plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, is another key element. Jupiter's enormous mass, powerful gravitational field, and influence provide a stabilizing effect on Pluto's orbit, blocking it from straying too far into Neptune's domain. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it unlikely that a catastrophic event will occur between Pluto and Neptune.